waveforms of PSK signal, okay, in time domain. And you know PSK modulator, you know PSK demodulator. Now similarly, how much bandwidth is required to transmit a PSK signal, right? Which is very simple. Now same. Now this is a binary data, binary 1 of a rectangular pulse, but of pulse width how much? TB. If a rectangular pulse whose pulse width is TB, then its Fourier transform is nothing but a sinc function of reciprocal to the pulse width. This is m of f. Okay. Now for binary 0, what about the binary 0? Binary 0 is also a pulse width of TB only. But this is a negative sign. Whether it may be a negative sign or a positive sign, the bandwidth does not affect. Bandwidth does not depend upon the phase. A bandwidth depends upon the range of frequencies, and a bandwidth depends upon the pulse width. The sinc function, the bandwidth of the rectangular pulse is a sinc. The Fourier transform of the rectangular pulse is a sinc. The bandwidth of the sinc function is inversely proportional to pulse width. But it may be a negative voltage or positive voltage is not the matter. Only the matter is what should be the pulse width. The pulse width is TB, bandwidth is 1 by TB. Pulse width is TB, bandwidth is 1 by TB. That negative side, this is the magnitude spectrum modulus, then you can take the positive side itself. Whether it is a binary 1 or a binary 0, whether it is a binary 1 or binary 0, pulse width is TB, binary 1 or a binary 0, pulse width is TB, therefore, so bandwidth is same 1 by TB. But what I want a Fourier transform of S1 of t. I want a Fourier transform of S2 of t. What is the Fourier transform of S1 of t? AC cos 2 pi ct. Now this is S1 of t or S2 of t. Now whose Fourier transform is, now this spectrum is shifted right side as well as this spectrum is shifted to right side as well as left side by an amount of Fc. Now that spectrum is shifted to Fc. Now this is Fc and Fc plus 1 by Tb, Fc minus 1 by Tb. This is for S1 of F, PSK spectrum, PSK signal in frequency domain. That is for S1 of t. What about for S2 of t? S2 of t is minus, but minus AC cos 2 FCT. Even if it is a minus or plus, what is the frequency? Frequency is same. What is S1 of t? S1 of t is AC cos 2 pi FCT. This is plus. What is S2 of t? S2 of t is minus AC cos 2 pi FCT. So S1 of t is plus AC cos 2 pi, S2 of t is minus AC cos 2 pi FCT. Whether this is plus or minus, it's not a problem. Only that depends upon frequency. Fc, frequency is Fc, carrier frequency is Fc. Whether it is plus or minus, it is a phase. But the bandwidth, power and bandwidth depends only on a frequency scale, frequency change, not the phase change. Okay. So this is S1 of f and this is S2 of f itself. Or for any confusion that is minus, so you can take this one. Modulus means same because frequency is Fc, so there is no change. This is S1 of f or S2 of f, and students are some of you are saying, sir, I can write like this, sir. You can write, not an issue. But is there any change in the frequency? That spectrum is also shifted to Fc, boundaries are same, then everything will be same. Okay, it's not a problem. That's what I'm saying. Whether it should be plus 10 or minus 10, power is not changing. Whether it is plus AC or minus AC, frequency is not changing. So bandwidth is also not changing. Okay. Now what is the bandwidth of PSK signal? So now the bandwidth of PSK signal is the bandwidth of phase shift keying signal Fc plus 1 by Tb minus of Fc minus 1 by Tb. Therefore 2 into 1 by TB, which is equal to 1 by TB, which is nothing but bit rate RB. This is a bandwidth of PSK signal. PSK waveforms in time domain, which we already completed. Now PSK waveform in frequency domain and spectrum. We call it as a spectrum. Okay, so this is a bandwidth required to transmit PSK signal. Okay, now we'll see the another digital modulation techniques. FSK, frequency shift keying. Frequency shift keying. What is a frequency shift keying? Frequency of the analog carrier is varied in accordance with binary data. Okay, what is the frequency shift keying? Frequency of the analog carrier is varied in accordance with binary data is called as frequency shift keying. Right? Now, FM modulator is what? What is FM modulator? FM modulator is nothing but the voltage to frequency converter. Is it right now? Now, these voltages are converted to the frequencies. This is FM modulator. Similar here is also. So the frequency shift keying, I am saying that similar to FM. So frequency shift keying means, so each voltage will be converted to a frequency. So this is also a voltage to frequency converter. Now whenever in your mind a voltage to frequency converter means, now one technique which we already completed. Now that is nothing but, now we use a voltage controlled oscillator. What we use? We use a voltage controlled oscillator, VCO, voltage controlled oscillator. Now to generate a FSK signal, so the binary data represented in non-return to zero form. The binary data represented in non-return to zero form. Now what is the non-return to zero form? Binary 1 is nothing but positive voltage, binary 0 is nothing but negative voltage. For easy convenience, this is plus 1 volt, minus 1 volt. Now this is a non-return to zero signaling. This is a non-return to zero signaling. Now VCO is internally generate one frequency is called as FC. So now what is the VCO output? Now see here, what is Fi? The frequency generated by VCO is Fi, which is equal to Fc plus Kv into M of t. Now which is nothing but F1, which is equal to Fc plus Kv into M of t. M of t message signal for binary 1 is nothing but plus 1 volt. Now which is nothing but F1, which is equal to Fc plus Kv. Now F2, what is F2? F2 equal to Fc plus Kv, M of t equal to, for binary 0 is minus 1 volt. Now which is nothing but F2, which is equal to Fc minus Kv. Okay. Now this is F1, F2. Okay. Now this is one frequency, this is another frequency. So can I write like this? This is S1 of t. What is S1 of t? S1 of t is nothing but AC cos 2 pi F1 into t. S2 of t, which is nothing but AC cos 2 pi F2 into t. This is F1 and F2. No change in amplitude, no change in phase, only change in frequency. Therefore, this is called as frequency shift keying signal, FSK signal. This is the FSK signal, frequency shift keying signal in time domain. Okay. Now thing here is, now this F1, which is nothing but Fc plus Kv, this is called as mark frequency. This is called as mark frequency. And this is Fc minus Kv. This is the low frequency. Compare with mark. Therefore, this is called as space frequency. Space frequency. This is mark symbol. Mark it. Now this is space. Okay. This is a mark symbol. This is a space symbol. Mark frequency, space frequency. So, sir, what is the meaning of this? So, if you transmit F1, so if you transmit F1, so the other end people will recognize that when F1 is received, which means that one mark is received. Suppose if you transmit F2, so other end people will recognize that now space is received and they will decode that. So mark space is nothing but A, mark is nothing but B, space mark is nothing but C, like this, for example. Okay, not exactly, for example. So this type of a code is called as Morse code. This is called as Morse language, Morse code. Okay, so actually all these things, amplitude shift keying, frequency shift keying, phase shift keying, this digital carrier modulation techniques actually used in, all these are used in, this digital carrier modulation techniques are used in telegraphy application. Used in telegraphy application. Now this is a Morse code. This mark frequency and space frequencies are called as Morse code. Morse key is a device transmitting Morse code. Morse key is a device transmitting Morse code, means it is transmitting frequency, it is shifting from F1 to F2. Am I right? It is sending F1 and F2. The process of sending F1 and F2 is called as keying. Okay, that is why this is actually frequency shift keying, amplitude shift keying. Now there is a transmitting of binary 1 and binary 0. Binary 1 and binary 0. Okay, this is the process of transmitting 1 and 0. The process of sending F1 and F2 is called as keying. Now this is the frequency shift keying. Actually, it is used in a Morse code. That Morse code, that language is used in the telegram and telegraphy application. Okay, so this is the transmitter portion. This is FSK transmitter. This is the FSK transmitter or FSK modulator. Now, what is FSK transmitter, FSK modulator output? There is no change in amplitude. There is no change in the amplitude. And amplitude wise, there is no change. There is no change in phase. Now there is a change in frequency. Now for binary 1 is a mark frequency, means high frequency. For binary 1 mark frequency, which is a high frequency. For binary 0 space frequency, which is a low frequency. This is S1 of t, this is S2 of t. Now this is the FSK signal. Now this is FSK wave, FSK signal in time domain. Okay, now note down, we'll see the demodulation process. Now here time period is very small, means high frequency. Time period is high, low frequency, F1, F2, but no change in amplitude, and there is no change in phase also. So only change in frequency, therefore this is called as frequency shift key. This is a high frequency because time period is low, F1. This is a low frequency, time period is high, F2. Now done. Now we'll see the demodulator. Now what is the demodulator in ASK and PSK? The demodulator in ASK and PSK is a coherent detector, because you want to use the same carrier which we are used at the transmitter with the same phase and same frequency. Now similarly here, but there is only one local oscillator, but what happened here? We want to use two local oscillators because here there are two different frequencies, F1 and F2. So I can design like this. The input to the receiver is an FSK signal. Now there are two local oscillators because there are two different frequencies are as output of the transmitter. Therefore this local oscillator will generate F1 frequency, and this local oscillator, now this second local oscillator will generate F2 frequency. Now this is an FSK signal, S1 of t and S2 of t. Now what is S1 of t? AC cos 2 pi F1 t, AC cos 2 pi F1 t. Here this is nothing but AC square by 2 plus AC square by 2 into cos 2 pi into 2F1 into t. Now use a low pass filter here, but the same signal is coming in this path. Now same, what is S1 of t? Now S1 of t, which is equal to AC cos 2 pi F1 into t. The same signal is coming in this path. Now this is nothing but AC square, AC into AC, AC square, cos A, cos B. What is cos A, cos B? 2 cos A, cos B, cos of A plus B plus cos of A minus B. So here you can get F1 plus F2, F1 minus F2. But this is the high frequencies. Now this low pass filter will not allow this particular signals. Now this is 0. What is the output of here? Now this is plus AC square by 2. Now this is 0. Now this is nothing but plus AC square by 2. So for S1 of t as an input to the demodulator, the output is plus AC square by 2. Where is S1 of t? Now this is S1 of t. So now the output of the demodulator is plus AC square by 2. Plus AC square by 2. Now for S2 of t, what happened? Now see here, what is S2 of t? S2 of t, which is nothing but AC cos 2 pi F2 into t. S2 of t is nothing but AC cos 2 pi F2 into t. So this is F2. Now here F2 plus or minus F1, but here F2 same. So this is nothing but AC square by 2 plus AC square by 2 into cos 2 pi into 2F2. This is not allowed by our low pass filter. Now here this is nothing but AC square by 2. Now here it is nothing but 0. 0 and AC square by 2. 0 minus AC square by 2. This is minus AC square by 2 for S2 of t. For S2 of t, now this is minus AC square by 2. This is minus negative voltage less than 0. Positive voltage greater than 0. So this is binary 1, this is binary 0, which is output of the demodulator. This is output of demodulator. Output of demodulator, which is whatever the transmitted signal, binary 1 and binary 0, you can get binary 1 and binary 0. Okay, this is FSK transmitter or FSK modulator, and this is nothing but now FSK demodulator or FSK receiver. Now this type of demodulation technique, which is called as coherent detector. Okay, this is a coherent detector. Okay, no doubt. Now we'll see what is the bandwidth required to transmit very simple, right? Because all are rectangular pulses, the bandwidth is nothing but sinc function. Now this is a binary 1 or binary 0. Pulse width is TB, so bandwidth is nothing but inversely proportional to pulse width. Now this is a rectangular pulse whose Fourier transform is inversely proportional to pulse width. But now this is an FSK signal whose Fourier transform is for S1 of t and for S2 of t. Now that spectrum is shifted right side by an amount of F1, because this is a mark frequency which is high frequency, F1 plus 1 by TB, F1 minus 1 by TB, this is S1 of F. Now for S2 of t, which is low frequency, because F2 is a low frequency, therefore this is, I can write nearer to the origin, this is F2, F2 minus 1 by TB, F2 minus 1 by TB, F2 plus 1 by TB. This is for S2 of F. This is the spectrum of FSK signal. This is the spectrum of frequency shift keying signal, FSK signal. So now what is the bandwidth? Now the bandwidth is the bandwidth of FSK, which is equal to F1 plus 1 by TB minus of F2 minus 1 by TB, F1 plus 1 by TB means F1 minus F2 plus 2 into 1 by TB H. This is the bandwidth of FSK signal. You want any comparison, and this is a negative shifting also, but negative frequencies I am not interested on here. So can you recollect your analog modulation technique? What is the bandwidth of FM in analog? The bandwidth of FM, which is equal to 2 delta F plus 2 into FM. Remember or not? 2 into beta plus 1 into FM or 2 into delta F plus 2 FM. So what is delta F? Can I write like this? Fi maximum minus Fi minimum plus 2 into FM. This is the bandwidth in the case of frequency modulation, FM. Because Fi max, which is equal to Fc plus delta F, Fi min, which is equal to minimum equal to Fc minus delta. Therefore, Fi maximum minus Fi minimum, which is equal to 2 delta F, is matching. So this is in case of FM, but what is in case of FSK? Now in FSK, now this Fi is nothing but, now this is bandwidth of FSK, which is nothing but, this is Fi maximum is nothing but F1, is correct? Now Fi minimum, which is nothing but F2 plus 2 into FM, that is the bandwidth of message signal. Now this is 2 into 1 by TP is nothing but RP, bit rate. Now this is bandwidth of FSK and bandwidth of FM. Anyway, both are a larger bandwidth. Okay, these are FM requires a larger bandwidth. Okay, no doubt. So what is a band pass data transmission? The band pass data transmission is nothing but it is transmitting baseband signal to band pass signal. Baseband signal means that ones and zeros, low frequency signals. Okay, so that low frequency signal will convert to a band of frequency. Okay, so this is a band pass data transmission is converting from baseband signal to band pass signal, low frequency information signal to modulated signal. So now we just just give a conclusion of all these things finally. ASK, amplitude shift keying signal. Okay, so in ASK the binary data is represented in ASK the binary data represented in on-off signaling, right? The binary data is represented in on-off signaling. Now, in PSK, the binary data is represented in non-return to zero signaling. Binary 1 is positive voltage, binary 0 is negative voltage. Now in FSK, in frequency shift key, binary data is represented in same non-return to zero signaling. Binary 1 is positive voltage, binary 0 is negative voltage. Okay, so another parameter is called as threshold voltage. What is it? Threshold voltage or threshold voltage represented by VTH or called as threshold set. Threshold voltage or threshold set. Now this is a threshold voltage or threshold set, which is nothing but, the definition of threshold voltage or threshold test is nothing but the average voltage levels represented for binary 1 and binary 0. So what is the voltage level for binary 1? What is the voltage level for binary 0? And average of that, 2 means by 2. So the average voltage levels represented for binary 1 and binary 0 is called as threshold voltage or threshold set. The average voltage levels represented for binary 1 and binary 0 is nothing but threshold voltage or threshold set. So now see here, what is the threshold voltage? Now the threshold voltage for ASK is V plus 0 by 2, V plus 0 by 2, which is nothing but V by 2. What is the threshold voltage for PSK signal? The threshold voltage plus PSK signal is V minus V by 2, which is equal to 0 volts. Now the threshold voltage for FSK signal, which is nothing but, now binary 1 is V, binary 0 is minus V by 2, which is equal to 0. This is the threshold voltage for ASK, FSK, PSK and bandwidth. What is the modulated signal? The modulated signal S1 of t, which is equal to AC cos 2 pi FCT, and S2 of t is minus AC cos 2 pi FCT. Now what is FSK? Now FSK is S1 of t, which is equal to AC cos 2 pi F1 mark frequency, S2 of t, which is equal to AC cos 2 pi F2 space frequency. Now here S1 of t, which is equal to AC cos 2 pi FCT, for S2 of t, which is 0 volts, because binary 0 is represented as 0 volts, right? And what is the bandwidth required to transmit a PSK signal? The bandwidth required to transmit a PSK signal is twice of bit rate. And what is the bandwidth required to transmit an FSK signal is, the bandwidth required to transmit an FSK signal is twice of bit rate plus F1 minus F2. And a bandwidth required to transmit an ASK signal is twice of bit rate itself. Okay. Now, in analog communication, signal to noise ratio is the performance indicator. Okay. In digital communication, I am transmitting binary 1. My receiver is receiving binary 1. Is there any error? No. I am transmitting binary 0. My receiver is receiving binary 0. Is there any error? No error. But I am transmitting 1, but my receiver is receiving 0, then the error is taking place. But I am transmitting 0, my receiver is receiving 1, then error is taking place. So a sequence of 1s and 0s are transmitting, then the same sequence is not possible to receive due to the effect of noise, then some information is lost. Therefore, then there is no exact transmission will be the reception due to the noise. Okay. So how much is the error probability? This is the 1s and 0s. Okay, when I am transmitting 1 is received or not, 0 is transmitting, 0 is received or not. Now the digital communication system performance indicator is error probability or bit error rate. Okay, probability of error or bit error rate, in detail we will see. Okay, in analog communication, the performance indicator is signal to noise ratio, or we call it as figure of merit. Signal to noise ratio at the output of the receiver to the signal to noise ratio at the input of the receiver, which we are already completed in the signal to noise analysis of analog modulation technique. Okay, so but now we are not completed the error probability concept, but I am giving one shortcut method. You can cross check once we completed that. So error probability should be less when the threshold voltage is less. Okay, what is that? When threshold voltage is less, error probability is less. What is the threshold voltage here? 0. So don't say error probability is 0, but probability of error is less. Here is also threshold voltage is 0, therefore error probability is less. Probability of error is less. But now here threshold voltage is V by 2, so probability of error is high compared with these two. Error probability is high. So for a best digital communication system, the error probability is 0 is good. If not possible, the probability of error should be as minimum as possible. The error probability should be as minimum as possible, but here the error probability is high. So you compare these analog, this coherent modulation techniques, then see here. Now here probability of error is less, but here bandwidth is very high. So you know that the best modulated signal is a signal whose bandwidth should be as minimum as possible. So based on this higher bandwidth, FSKs are not used practically. FSK is not used practically. FSK is not used practically because of higher bandwidth. This is the higher bandwidth reason. Now this is not used. Now ASK, see here, ASK is also not used because probability of error is high. The probability of error should be as minimum as possible. So we don't get a higher probability of error. Probability of error should be very less. But here bandwidth is less, but error probability is high. That's why ASK is also not used. Therefore now you see here bandwidth is 2 times of bitrate is less, and error probability of error is also less. Here error probability is less, but bandwidth is more. Here bandwidth is less, but error probability is high. Therefore now you compare these three techniques. Now you tell me, practically in most of the applications PSK is preferred because bandwidth is less and error probability is also less. Understand not? So based on error probability and bandwidth, most of the applications PSK is used. Okay. Now the demodulator is, what is the demodulator? The demodulator is coherent detector. Here the demodulator is nothing but coherent detector. Coherent detector. Now the demodulator is a coherent detector, but you know the problems what we are faced in the coherent detector. If there is any phase mismatch, quadrature null effect, is there any frequency mismatch, beating effect will be taking place. Am I right or not? So that is a problem in the case of all these three digital carrier modulation techniques. All these three band pass data transmission suffers with demodulation, which is nothing but coherent demodulation, where the quadrature null effect or frequency effect is taking place. Now phase mismatch and frequency mismatches are taking place. Okay, this is the disadvantages of this modulation technique. That is the reason why this is called as coherent ASK, coherent FSK. Now this is coherent PSK. Okay. Now this is also called as coherent ASK, coherent PSK, coherent FSK. Don't confuse. That is nothing but normal ASK, FSK, PSK only. Okay. Now this is the comparison of ASK, PSK, and FSK. And finally we vote for PSK based on the bandwidth and probability of error is less. Note on this. Now we'll solve one problem based on this. Now see the question, a voice signal, now your question. Now a voice signal sampled, quantized and encoding. How we can say? He says that PCM, and here he is giving 8-bit PCM, means 8-bit A to D converter, means n value is 8. Now what is asking? A voice signal is sampled at the rate of, a voice signal is sampled at the rate of, this is a voice signal which is given. A voice signal is sampled at the rate of, sampling rate is given. The voice signal is sampled at the rate of 8,000 samples per second, 8 kilo samples per second. And each sample is encoded into 8 bits. Each sample is encoded into 8 bits using PCM. What is mentioned? Each sample is encoded into 8 bits using PCM. The binary data is transmitted into free space with a different modulation technique. The binary data is transmitted into free space after modulation. Okay. So this is after modulation, it is transmitted into free space, and he is asking to find bandwidth of the modulated signal, and the modulation process used is, first we want to find, this is sampling, quantization, encoding, means PCM. What is the bit rate of PCM system? Bit rate of PCM system RB, which is equal to 1 by TS into N. What is 1 by TS? 8 kilo into N. What is N? 8, which is equal to 64 kilo bits per second is the bit rate in a case of PCM system, because he has already mentioned PCM, sampling, quantization, encoding. Now, what is the bandwidth after modulation? What is the modulation he is given? He is giving, the first modulation is amplitude shift keying, second modulation is phase shift keying, third modulation is frequency shift keying. Then he is asking to find what is the bandwidth here, what is the bandwidth here, and what is the bandwidth there. So now you tell me what is the bandwidth. Now the bandwidth in ASK is twice of bit rate. If it is amplitude modulation, the bandwidth required is twice of bit rate is already calculated, PCM 64 kilo. So the bandwidth, which is equal to 128 kilohertz, is the bandwidth required to transmit this information with the help of amplitude shift keying technique. Now, how much bandwidth required for PSK? So the bandwidth required for PSK, you know that the bandwidth required to transmit PSK signal is twice of bit rate. So which is nothing but twice of bit rate is 64 kilo. Therefore, bandwidth, which is equal to 128 kilohertz. Now, what is the bandwidth required to transmit FSK? The bandwidth required to transmit FSK is bandwidth which is equal to twice of bit rate plus F1 minus F2. So the bandwidth which is equal to twice of bit rate is 64 kilo plus F1. Mark and space frequency is also given in the question. What is the mark frequency is given? The mark frequency is mentioned as 10 megahertz, and space frequency is mentioned as, the mark frequency is mentioned as 10 megahertz and the space frequency is mentioned as 8 megahertz. So this is mark frequency 10 megahertz minus space frequency 8 megahertz. Therefore, the bandwidth, which is equal to 2.12 megahertz. So this is a practical application, you can easily understand. See here. Now this is same, sampling, quantization, encoding, and after modulation you can cross check. So ASK require how much bandwidth? 128 kilohertz. PSK required how many bandwidth? 128 kilohertz. FSK required how many bandwidth? 2.12. Very high bandwidth, huge bandwidth. That's why because of the huge bandwidth, practically not used. Practically not used because of higher bandwidth. But here bandwidth is 128 kilohertz. Here bandwidth is also 128. Both are smaller bandwidth. But why ASK is not used? Because here error probability is high. But here error probability is less. That is the reason why, based on these two parameters, now this is preferable practically. Understand or not? Now this is with a practical example I am explaining. Okay, you can easily understand. Note on this.